Well, in this video, we're going to be discussing power series. We're going to first start by power series that are centered at 0, and then we're going to generalize to power series that are centered at A. Now, if we look at power series centered at 0, these are sums in the form of sum when n goes from 0 to infinity of Cn times x to the n. Now that is the general term of the series, of the power series centered at 0. Now Cn in fact is a real number. That's the coefficient of the term corresponding to x to the n for each value of n, and x to the n is in fact a power of x, and we'd like to note again that n goes from 0 to infinity. N in fact is a natural number here. So whenever you can write a series in this form, that would be a power series where the terms in the sum are in the form a constant times a power of x, where the powers of x go all the way to infinity. Now, so these are power series centered at 0. Now, of course, the power series do in fact have an interval of convergence and a radius of convergence. Now, the interval of convergence, negative r. So over here, the radius of convergence would actually be r. Now, what do interval of convergence and the radius of convergence imply to the series? Now, we know that these series are in fact used to approximate functions. So whenever I have a function f of x that is approximated in fact by this power series, whatever the function is, so we're just speaking the general case here. So whenever we have a function f of x that is in fact approximated by a power series, over here, if we first start by graphing the function that represents f of x, now the interval of convergence, suppose that we have negative r. The interval of convergence would actually mean that inside this interval, this power series approximates well the function, which means that if I draw a polynomial, you know that power series are in fact polynomials. So if I draw the polynomial representing the power series, if I draw the series over here, representing the graph representing the polynomial of the series. So over here you'd notice that between negative r and r, the two curves almost converge to each other. They're almost the same. So the power series would in fact approximate well that function inside that interval. However, outside that interval, the power series would not be a good approximation to that function. So this is in fact one use of power series. It is in fact whenever we aim to represent a function by a power series, we have to determine the radius of convergence or the interval of convergence. We'd have to know that this function is well approximated by that power series over which interval. Now over here, just before we move to the following example, let's just try to make sense of the procedure or the process that we will actually adopt in solving the next example. So if we look at the power series, the general term of a power series does remind me a lot of that of a geometric series, because we know that geometric series are in fact series that can be written as the sum of a term, a first term or a coefficient, times r to the n. Now this is the general term that represents a geometric series. However, you'd notice that these, in fact, they look like each other. But however, here what is represented by R, the common ratio of the geometric series, is in fact variable for the power series. And we know that geometric series, whenever the common ratio is smaller than 1, they do have a limit or a finite sum, which is equivalent to the first term, if the first term here is to be A, over 1 minus R. So over here, we're going to, in fact, the functions that we need to aim to write in terms of power series, we're going to aim to write them in terms of functions that are written in the form a constant over 1 minus a variable quantity, since what is corresponding to the common ratio in a geometric series is in fact a variable for the power series. So whenever we could write a function in this form, even if R is variable, we would then be able to write it in terms of a power series, in addition to determining the interval of convergence of that series because of the condition that we already have here. Okay, so if we go to the next example, we need to find a power series that represents the function y equals to 1 over 1 plus x over the interval negative 1, 1. Now over here we are already given the interval of convergence, but we're going to justify it and determine it so that we would know why it is in fact negative 1, 1. So by looking at example 1, so we have the function y equal to 1 over 1 plus x. Now we can see that this function can be written in the form 1 over 1 minus negative x. So as I've told you just earlier, we need to aim to write functions in the form 1 over 1 minus r in order to be able to determine the radius of convergence. And of course, write the function or represent it in terms of a power series. So over here, we know in fact that y, being able to write it as 1 over 1 minus negative x, we could see this as a geometric series where the first term is 1 and the common ratio is negative x. So we could in fact see this. I'm going to write this as a geometric series, but it would not be a geometric series. But we do this analogy in order to be able to write the function as a power series. So we look at this as a geometric series where the first term is 1 and the common ratio is negative x. So over here, the function can in fact be written as y equals to the sum where n goes from 0 to infinity of the common the first term, which is 1, and the common ratio, which is negative x to that. So over here, the common ratio being negative x, we need to, in fact, determine the interval of convergence. So we know that a series, a geometric series, is convergent if its common ratio is smaller than 1. So by considering negative x to be smaller than 1, and we know that the absolute value of negative x is the same as the absolute value of x, so it's the absolute value of x smaller than 1, then x is between negative 1 and 1, and this is why the interval of convergence of the power series representing this function is negative 1, 1. So over here, the function would actually be represented, we can write this in this form, negative 1 to the n times x to the n. So this is the power series representing the given function, okay, with an interval of convergence -1, 1, and with a radius of convergence equals to 1. However, if we look at part 2, in part 2 we have a power series. We want to find a power series that represents the function y equals to 1 over 1 minus 2x. Now again, if we do the analogy with 1 over 1 minus r, in fact we'd see that this is written in the form 1 over 1 minus r with r equals to 2x, and we can actually see that the first term is 1 and the variable common ratio is 2x. So over here the function can in fact be written as the sum that goes, where n goes from 0 to infinity, of the first term, which is 1, and the common ratio, which we're denoting here as r, is 2x. So over here you could just in fact split this, but however, if we were to first determine the interval of convergence, which is already given in the given, but we're going to determine it anyway, that's for the common ratio, which is 2x here, to be smaller than 1. So absolute value of x to be smaller than half, so x would in fact be between -half and half. So over here the interval of convergence is -half, half, and the radius of convergence is half. So over this interval, this function is well approximated by this series, which you could in fact write as 2 to the n times x to the n. Okay. Now, if we were to generalize this, we'd have a power series centered at A, which is in the form Cn, where Cn is still the real coefficient corresponding to the nth term. So Cn into, instead of x to the n, I have x minus a to the n. So a power series centered at 0 is in fact this one for a equals to 0. So this is the generalization. This is the power series centered at A. So in fact the expansion would be similar. It would be C0 plus C1 into x minus a plus C2 into x minus a all squared, etc. all the way to n at infinity. So the interval of convergence of the series would in fact be a minus r, a plus r, where r is the radius of convergence. So over here, instead of being centered at 0, we're adding and subtracting r to a in order to determine the interval of convergence. And that is because when we are representing functions by power series centered at a, we aim to have the function written in the form 1 over 1 minus a quantity in the form x minus a, where this plays the role of the variable common ratio, and when the absolute value of x minus a is smaller than 1, it would eventually lead us to this interval. So over here, we need to find in each case a power series to represent f of x, stating the interval and radius of convergence. Now, if we look at f of x, again, we need to aim to write the functions in the form u1 over 1 minus r in order to be able to represent these functions in terms of power series. So over here, f of x is equals to 1 over x. So aiming to write it in this form with a denominator in the form 1 minus r, we could in fact write f of x as 1 over 1 plus x minus 1. So we could start with this as a first step. So over here, we do have the 1 plus, and don't forget the plus is a double negative, so it is 1 over 1 minus negative into x minus 1. So our variable common ratio here is negative into x minus 1. So over here, aiming to write this in the form of a power series, that would in fact be f of x. Now the first term is 1, so that would be n goes from 0 to infinity of negative into x minus 1 all to the power of n, which is in fact the sum where n goes from 0 to infinity of negative 1 to the n times x minus 1 to the n. So this is the power series representing the function. Now if I were to determine the interval of convergence, I would in fact have to consider the common ratio smaller, its absolute value smaller than 1. Now, so the absolute value of negative into, we know that the absolute value of negative a is the same as the absolute value of a. So in fact, we'd have here the absolute value of x minus 1 smaller than 1, or the absolute value of 1 minus x smaller than 1 if you were to expand that negative. But they basically lead you to the same answer anyway. So x minus 1 would in fact be between negative 1 and 1. So x would be between 0 and 2. Don't forget that this is a power series centered at 1. 1 is the center of this series. So 1 is the center of the interval 0, 2. So the radius of convergence is in fact 1. So I would in fact be the interval 0, 2, and the radius of convergence is 1. So if we were to look at the second series, now the second series, the second function. Now the second function can be in fact looked at in two different ways. We can in fact look at this as if it's in the form 1 over 1 plus x, and then factor out a negative here, write this plus as a double negative. Or we could in fact look at this in the form half over 1 plus x over 2. And then in that case, with this one would actually be a power series centered at negative 1, while this one would be a power series centered at 0. So you could go either ways. Eventually, each will have its corresponding radius of convergence, and for each of the two forms, or for each of the two series corresponding to each form, the radius of convergence would actually allow that series to converge to the function over that interval. So basically, it doesn't really matter here which one you choose, because each form would actually have its corresponding radius of convergence. So I'm going to personally go for the second one because it's easier to work with series centered at 0. So over here, f of x would in fact be seen as half over 1 minus negative x over 2. And by the way, this form is determined by factoring out the 2 at the denominator. When you factor out the 2 at the denominator, then the 2 goes up as a half on the numerator, which leaves you with 1 plus x over 2 at the denominator. Okay, so over here, this can in fact be written as a series in the form, the sum where n goes from 0 to infinity of half, we should not forget the half, times negative x over 2 to the n, because don't forget, when it comes to geometric series, the sum, the general term of the sum has in fact u1 times r to the n. So you should not forget the half. Over here, the first term is not 1, the first term is half. So over here, You could keep the negative with the x over 2. You could just take this out. It doesn't really matter. So by rearranging this, we'd get the sum in the form where n goes from 0 to infinity of -1 to the n over. I have a 2 with a 2 to the n, that's 2 to the n plus 1. This whole term plays the role of Cn in the general form of the series times x to the n. So in order to write it as a power series, you need to eventually reach that form, a Cn times x to the n. So it has to be a power of x times its corresponding coefficient in terms of n. However, to determine the interval of convergence, you'd actually refer to the term that you consider to be as r, so which is -x over 2 in our case. So the absolute value of -x over 2 is the same as the absolute value of x over 2, smaller than 1. So over here, the absolute value of x would be smaller than 2, so x would be between -2 and 2. Don't forget, this is a power series centered at 0, and 0 is the center, so the 0 should be the center of the interval. Similarly here, we use the power series centered at 1, so 1 should be the center of the interval of convergence. So the interval of convergence in this case would be -2, 2, and r would actually be 2, because the distance between the center of the interval and the bounds of the interval is in fact 2 units. You would in fact follow the same steps if you were to use this form, but in that case you'd be working with a power series centered at -1. So the interval of convergence has to be, in that case, an interval centered at -1. Now, if we look at f of x here, you'd notice that we have x squared over 2 plus x. However, we need it in the form a constant divided by 1 minus r, even where r is a variable common ratio. So over here, what we could do is just write it in that form. We can see this function as x squared over 1 over 2 plus x. So what we would do here is determine the power series that represents 1 over 2 plus x, and then multiply it by x squared. Multiply that expansion by x squared. So if we look, 1 over 2 plus x is the function from the previous part that we already determined the power series representing it. So over here, f of x would actually be, whenever you're working on an exercise, if you've already represented a function using a power series and you encounter that function in a later exercise, you can use the power series you obtained in a previous part. However, if we did not have here part 2, you would have to actually re-look for the power series representing 1 over 2 plus x all over again. So that would be x squared times the sum where n goes from 0 to infinity of -1 to the n over 2 to the n plus 1 times x to the n. So basically here, x squared, now the variable of the sigma is n, so x squared is in fact independent from that variable, and x squared multiplying the sigma, it means that x squared multiplies each term in that sum. So it's as if I have a sum where I'm expanding x squared into it. So in that case, that would lead us to expanding the x squared into the sum. That would lead me to -1 to the n over 2 to the n plus 1 times x to the n plus 2, because x to the n times x squared is x to the n plus 2. So this is the power series that is in fact representing f of x in part 3. However, regarding the interval of convergence, since f of x is in fact x squared times 1 over 2 plus x, then f of x, the power series that represents it, would in fact take the same interval of convergence of the power series representing 1 over 1 plus 2x. So over here, I would still be -2, 2, with radius of convergence equals to 2. Okay? Now, over here, if we have a power series centered at A, so to determine the interval and the radius of convergence of the series, the ratio test is applied. By considering AN to be the general term of the series, we consider L to be the limit when n is approaching positive infinity of an plus 1 over an. Now, if we refer to the previous examples, we already had the functions. That we were writing them in the form a constant over 1 minus r, and then take that variable r in absolute value smaller than 1 to determine the radius of convergence or the interval of convergence. However, here in this section, what we're doing is the other way around. We're starting with a power series, and we're trying to reach a function that is represented by a power series under the obtained interval of convergence. So over here, we're starting with the series. So over here, we don't have the function in the form 1 over 1 minus r in order to say I take r, its absolute value smaller than 1, and determine the interval of convergence. Over here, what you have is the series. You're starting with a series in order to eventually represent it by a function. So over here, whenever you are starting with a series, in order to determine the radius of convergence, you start by applying the ratio test. So you consider L, the limit when n goes from n to positive infinity of the absolute value of an plus 1 over an. Now that is the ratio test. So over here, L in fact would be the absolute value of a certain function of x, since an is a function of x. So over here, L would actually be the absolute value of the function of x. So to determine the interval of convergence, what you would do is consider L smaller than 1, because we know by the ratio test a series is convergent if L is smaller than 1. So by solving this inequality for x, you'd actually determine the interval of convergence. So, however, if you have L to be a real number, in that case, the radius of convergence would be 1 over L. Okay, so for example, if you end up with a limit to be infinity, then the radius of convergence is 1 over infinity, which is 0. So a radius of convergence equals to 0. It means that the two functions, it means that the power series is not a good representative of its corresponding function, because there's no radius of convergence, there's no interval of convergence there due to the radius of convergence being equals to 0. However, if, for example, L is 0, then R would be 1 over 0, which is infinity. An interval of convergence being equals to negative infinity, positive infinity, which is all R, it means that the power series approximates well its corresponding function over all R. Okay? So over here, we need to determine the radius and interval of convergence of each of the following series. Now you can see that these are in the form Cn x to the n, where Cn in this case is 1 over n squared. So this is in fact a power series. However, this one starts from 1 because for n equals to 0, 1 over n squared is not defined. However, to determine the radius of convergence, we start by finding L, which is the limit of the ratio an plus 1 over an according to the ratio test. So L would in fact be the limit when n is approaching positive infinity of an plus 1 over an, of course, where an is 1 over n squared times x to the n, or x to the n over n squared. Okay, so L would in fact be the limit when n is approaching a positive infinity of the absolute value of an plus 1, that would be x to the n plus 1 over n plus 1 all squared, divided by an, so that's multiplied by the reciprocal of an, so that's n squared over x to the n. So over here, that would in fact be the limit when n is approaching positive infinity of x, because over here x to the n plus 1 divided by x to the n is x, times n squared over n squared plus 2n plus 1. Now I did expand at the denominator to show you the term with the highest degree, because over here this is a quotient of polynomials at infinity, so to determine the limit here we'd actually have to find consider the terms with the highest degree. So the terms the highest degree both being n squared, this expression has in fact a limit equals to 1. So L would in fact be, if we were to actually write that and not just jump to the final answer, that would be x of n squared over n squared. So that would be the n squared cancelled out, and we would obtain absolute value of x for L. So L is smaller than 1, then the absolute value of x is smaller than 1, which leads to x between -1 and 1. So the interval of convergence would actually be -1, 1, and the radius of convergence would be 1. However, for the other one, we'd start by considering L to be the limit when n is approaching positive infinity of an plus 1 over an, where of course an is the general term of the series, that's -2 to the n, x to the n over the square root of x plus 1. So L is the limit when n is approaching positive infinity of the absolute value. Now the absolute value is really important here, so you could end up determining the interval and the radius of convergence. So make sure not to forget the absolute value. So that would be -2 to the n plus 1 times x to the n plus 1 over the square root of x plus 1 times that's n plus 2. I did copy it off here, so over here I copied it wrong. This should be an n, not an x. So times the square root of n plus 1 over -2 to the n and x to the n. Now over here, the powers, simplifying the powers, would actually end up with, now over here, that square root of, we can combine the two square roots, so that's a square root of n plus 1 over n plus 2 times, now over here, -2 to the n plus 1 divided by -2 to the n, that would leave me with -2, and x to the n plus 1 times x to the n, that would leave me with x. However, at infinity, over here, looking inside the square root, the terms of the highest degree would be n over n. So over here, this has a limit of 1 at infinity, which would leave me with L being equals to the absolute value of -2x, which is the same as the absolute value of 2x, because the absolute value of -a is the same as the absolute value of a. So L being smaller than 1 would actually lead to 2x smaller than 1, absolute value of 2x smaller than 1. So absolute value of x smaller than half. So x would in fact be between -half and half. So over here in this case, the interval of convergence would be negative half half, and the radius of convergence is half. Now, over here in this theorem, we are still considering a power series centered at A. So what they're saying is that if the series is convergent in an interval A minus R, A plus R, where R is positive, then the derivative of f of x, over here f of x is representing the series. So f prime of x would still be a power series, but would be represented by the derivative of the terms in the power series. So this is where the n, x minus a, n minus 1 comes from. It's because that is the derivative of x minus a to the n. X minus a to the n is in the form u to the n, so its derivative is nu to the n minus 1. So over here, f prime of x would still be a power series, and it would still be convergent in the same interval of convergence as the original series. And if f is convergent for all x, then f prime would also be convergent for all x. So f of x and f prime of x would actually be convergent in the same interval of convergence. Okay, so how could we actually use this? For example, if we look at this example here, we have to find a power series representing each of the following functions. So if we look at the first one, f of x is arctan of x. If we go back to what we did at the beginning of this video, we were aiming to write functions in the form a constant over 1 minus r, where r is a variable common ratio, so that we could write them as power series, right? However, if we look at arctan, there's no way I can write arctan in the form 1 over 1 minus r, or a constant over 1 minus r. But I do know that the derivative of arctan is 1 over 1 plus x squared. So the derivative of arctan can be written in the form of a constant over 1 minus r. So f prime of x here could be represented by a power series using the same method we've used earlier. So, and according to this theorem, it says that a series and its derivative series have the same interval of convergence. So by finding the power series corresponding to f prime, its interval of convergence and its radius of convergence, eventually I could go back to f of x by integrating and then considering the same interval of convergence and radius of convergence for f of x as the one we found for f prime. So over here, f prime of x is 1 over 1 plus x squared, which can be written as 1 over negative into negative x squared. Excuse me, over here the square is inside the parentheses. I'm going to be rewriting this. Okay, so over here we can look at this as a geometrical series with a first term equals to 1 and a variable common ratio equals to negative x. So over here, f prime of x can in fact be written as the sum where n goes from 0 to infinity of the first term, which is 1 here, times the common ratio, which is negative x squared to the n. I'm sorry, I rewrote the square outside the parentheses. It should be inside so that these two would be equivalent. Okay, so it's negative x squared to the n. So here this can be written as negative 1 to the n times x to the 2n. So this is the power series representing f prime. Now, before I go back to f of x, I need to, in fact, determine its interval of convergence. So we do have here that the absolute value of negative x squared should be smaller than 1, which is equivalent to x squared smaller than 1. So x squared is between negative 1 and 1. However, x squared greater than negative 1 is always true. So that is the equivalence of x squared being smaller than 1, because x squared greater than negative 1 is always true. So over here, x squared smaller than 1, then x would be between plus or minus the square root of 1. But over here, the square root of 1 is 1. So that would be negative 1 and 1. So the interval of convergence is negative 1, 1. And the radius of convergence is 1. However, I need to go back to f of x, because my point is not f prime. My point is f of x. I need to find a power series that represents arctan of x. But having found a power series representing f prime, then I could in fact go back to f prime of x. So f of x would basically be the integral from 0 to x of f prime of t dt. So over here, all I have to do is just integrate these. So integrating the terms of the derivative one by one, that would in fact leave me with f of x being equals to the sum, where n goes from 0 to infinity, of negative 1 to the n. Now integrating this is x to the 2n plus 1 over 2n plus 1. Okay, so that would be between 0 and x. Of course, upper bound minus lower bound, that would, for t equals to 0, that would in fact be 0. So we're just left with the upper bound. So that is the sum where n goes from 0 to infinity of negative 1 to the n over 2n plus 1 times x to the 2n plus 1. So this is f of x with the same interval of a convergence, negative 1, 1, and the same radius of convergence, 1, as its derivative. Now, if we look at f of x in part 2, now in part 2, we are given the function f of x equals to x arctan and centered at 0. Now, over here, as you can see in the previous part, we have written arctan of x as a power series centered at 0. So we could just use it here. Okay, and x arctan would have the same radius and interval of convergence as arctan, because over here I'm just multiplying by x. It's independent from n, which is the variable of the series. Okay, so over here f of x would in fact be x times the sum where n goes from 0 to infinity of negative 1 to the n over 2n plus 1 times x to the 2n plus 1. So expanding that x into the sum would leave you with the sum where n goes from 0 to infinity of negative 1 to the n over 2n plus 1 times x to the 2n plus 2. So this is the power series representing x arctan of x, with the same interval and radius of convergence as arctan, which is negative 1, 1, and the radius of convergence would actually be 1. However, if you have not found earlier the power series representing arctan of x, then in that case you just leave the x aside for some time, and you just find the power series representing arctan of x the same way we did in part 1, and then eventually multiply it by x the same way we did here. We're going to solve this last example. So I'm sorry, we have this theorem before the last example. So if we are given two power series centered at A, now it's very important that whenever over here you are applying this theorem, that the two series would be centered at the same number. So we have f of x to be centered at A and g of x to be centered at A as well. So each having its corresponding radius of convergence. So I'm going to refer to R of f as the radius of convergence of f of x, and by R of g the radius of convergence of g. So, however, whenever you perform operations of these power series, for example, if I add f and g, or subtract f and g, or multiply f and g. Now, over here, the sum, the product, and the product and the difference would also be a power series. However, instead of looking for the interval of convergence from the start, you could actually deduce the radius of convergence of the different operations of these two series from the radius of convergence corresponding to each series. For example, here it says that the radius of convergence of the product of f and g and the sum and difference of f and g would actually be the minimum between r and f and r of g. And that is because the interval of convergence of these series would actually be obtained by intersecting the interval of convergence of f and g. So this is why for the radius of convergence we usually go for the minimum radius. However, f of k of x, which means that if instead of x minus 1 I have a 2x minus 1, that would in fact have the same radius of convergence as f. Now, if we were to do this example, now show that f of x can be written as 7x minus 2 over x squared minus x minus 2. That f of x can be written as 3 over x plus 1 plus 4 over x minus 2. However, in order to show this or verify this, all you have to do is just take this and reduce the same denominator, and by reducing to the same denominator you'd obtain 3 into x minus 2 plus 4 into x plus 1 over x plus 1 into x minus 2. So simplifying, at the numerator 3x plus 4x, that's a 7x, and minus 6 plus 4, that's a minus 2, over expanding the denominator, that's x squared minus 2x plus 1, that's a negative x minus 2. Okay, so basically you can see that their sum is equals to f of x. However, over here, the point behind part 1 is just to be used for part 2 to make the work a lot easier. So in part 2, they're asking us to find a power series centered at 0, where the interval and radius of convergence are to be determined. Of course, again, whenever we need to find or represent a function by a power series, we always aim to writing that function in the form a constant over 1 minus r. However, if we look at f of x here as given, that is practically impossible to write in that form. However, using the sum of these partial fractions, you could in fact represent each as a power series, because each is in the form a constant over 1 minus r, where r is a variable. So each could be represented by a power series. So I can determine the interval and radius of convergence of each, and then when you add these two series together, you would intersect in fact intersect the interval of convergence of these two to determine the interval of convergence of f. So this is how it will basically go. So over here, if we start with I'm going to call this g of x as 3 over x plus 1. Now this can be written as 3 over 1 minus negative x. So g of x is in fact the sum where n goes from 0 to infinity of the first term, which is 3, times negative x to the power of n. So writing it in the form cn times x to the n, that would give me 3 into negative 1 to the n times x to the n. However, this is a power series centered at 0. To determine the radius of convergence, we go for the absolute value of r smaller than 1. Now, r here is negative x, and the absolute value of negative x is the same as the absolute value of x. So that's the absolute value of x smaller than 1. So x is between negative 1 and 1. So I'm going to call this I of g. So this is the interval of convergence corresponding to g. That's negative 1, 1. And the radius of convergence of g is, in fact, 1. Doing the same thing for the other one, which I'm going to call h of x. So h of x is 4 over x minus 2. So over here, I need to, don't forget that it's true that here I can write this as 1 plus x minus 3. However, I want the power series to be centered at 0, so what we would do is the same thing we did earlier, is factor out a negative 2. So by factoring out a negative 2, that would leave me with 1 minus x over 2. Right? So that would be 4 over negative 2, that's a negative 2 over 1 minus x to the 2. So h of x can in fact be written as a power series in this form. It's a sum where n goes from 0 to infinity of the first term, negative 2, times what is in fact represented as the common ratio here, which is x over 2. So that is x over 2 to the n. So writing this in the form cn times x to the n, that would in fact leave me with the sum from 0 to positive infinity of 2 over 2 to the n. That would leave me with 1 over 2 to the n minus 1. So that is negative 1 over 2 to the n minus 1 times x to the n. So determining the interval of convergence of this power series, we would in fact take the absolute value of x over 2 smaller than 1. So the absolute value of x smaller than 2, so x between negative 2 and 2. So which leaves me with I of h, the interval of convergence corresponding to h, as negative 2, 2. And then the radius of convergence being equals to 2. However, going back to f of x. Now, regarding f of x is in fact the sum of g and h. So f of x being equal to g of x plus h of x. So f of x is the sum where n goes from 0 to infinity of 3 times negative 1 to the n x to the n plus the sum where n goes from 0 to infinity of, what was it? Negative 1 over 2 to the n minus 1 times x to the n. So f of x is in fact the sum, since over here we do have the same range of values for n for both series, we can combine and add the two general terms, since sigma is linear with respect to addition. So that would in fact be 3 times negative 1 to the n minus 1 over 2 to the n minus 1. All of this times so all of this times x to the n. Okay, so we have to write it in the form c of n times x to the n. However, regarding the interval of convergence, the interval of convergence would actually be I of g inter I of h, so the intersection of the interval of convergence of g and h, which in this case, I of g being a subset of I of h, so that's negative 2, 2. Negative 1, 1. So it's negative 2, 2 intersecting negative 1, 1, which is negative 1, 1. And the radius would actually be 1, which notice you ended up by having the minimum radius as a radius of convergence of f. So he basically, since the two power series are centered at the same number, then one interval of convergence will always be a subset of the other one. So this is why over here for the radius of convergence we take the minimum radius of convergence, and over here, since the interval of convergence would be the intersection and both being centered at the same number, then one of them is a subset of the other one. So this is why we always go for the smaller interval.